Okay, thank you very much, Martin. No pressure there. So, I'd like to start by saying thank you all for being here. I'm going to begin by explaining the title of this talk. So, those of you who have children or grandchildren of a certain age probably know where I've borrowed this title from. But for the rest of you, it comes from a book, and now a film. And this book and this film are very popular with a certain 4-year-old boy who lives in my house. And normally, in about an hour's time, I'd be reading him a bedtime story. And when I was planning the inaugural lecture, I thought, well, that's a shame, I won't be able to. Then I thought, maybe I can, if I combine my inaugural lecture with a bedtime story. So that's the theme. This is going to be a bedtime story, and the title is The Scientist in an Adventure with Rocks, Oil, Water and Volcanoes. You can fall asleep if you want to. I hope you won't, but it's fine if you do. What I'm going to talk about is not some big picture kind of state-of-the-art thing. This is my talk. I'm going to be quite selfish. I'm going to talk about things that I find really interesting. So what you'll hopefully see is a flavour, a snapshot of the research that I do at the moment and have done over the past few years. What I'd like to begin by doing is telling you a little bit about how I got to be here in the first place. See if I can make this to a pointer work. How did I go from being a small boy to being a professor at Imperial College? So if you're sitting comfortably, I'll begin. A long, long time ago, in a galaxy far, far away, or in fact Liverpool, there was a small boy who had a dream. That's the wrong talk. Who thought that when he grew up, he'd like to be a professor at Imperial College. Now, as ever with these stories, the road is not smooth, there are diversions, you go down the wrong track. So occasionally, I forgot this mission. So I thought that maybe I'd like to be a train driver. But you know, really the glamour of that job is probably past. I thought I might follow my father and have a career in the merchant navy. You know, it's pretty rough at sea sometimes. You have to have a strong stomach for this kind of thing. There was an early appearance on television. This is the World Snooker Final in Preston in 1998. This was filmed during the BBC Children in Need. You can see Pudsey Bear just there. This was my first and so far only television appearance. And I was dressed as a chicken. So perhaps not a TV career. So having completed, as Martin said, a physics degree here, I found myself at the University of Liverpool doing a PhD. This is when I was introduced to geology. I was also introduced to geological fieldwork and the importance of a balanced diet, including plenty of fluid intake to maintain oneself in tip-top physical condition. Then I found myself back at Imperial College in the then Department of Earth Resources Engineering, and I was standing on a beach on the Isle of Wight in driving rain, looking at some cliffs, and the question is, why was I there? And that takes me on to the first chapter of our bedtime story, Rocks and Oil. So what I'd like to start by doing is just pointing something out which people might not be aware of, which is that we actually don't do a particularly good job of producing oil at the moment. So what I have here is a plot of a few example reservoirs. What you can see here is we have what's called the recovery factor plotted on this axis here. This is the fraction of oil that we think is in the ground that we actually produce to surface. And that's plotted against something called net to gross. That's the fraction of the reservoir which actually has oil-bearing rock in it. And we can think of that as being a kind of a proxy for geologic complexity. This would be a rather simple reservoir. Geologically, this might be a rather complicated one. As we'll see, my interest very much lies in understanding geological complexity and how it impacts on oil production. But the key feature of this figure that I want you to notice is that most of these recovery factors are below a half. So we're only producing about less than a half of the oil that's in the reservoir. Put another way, we're leaving more than half of it in the ground. So this is clearly not a very efficient use of resources. Can we do better than this? Now there are groups all over the world who are looking at this, and there are many reasons why we don't produce more than or a higher proportion of the oil than you see in this figure here. My particular interest is in what control geology plays in how we can recover oil from underground. So in that context, we need to think about what we need to be able to do to predict oil recovery. We need to have a model that can predict how fluids flow, how oil and gas flow through rocks to a producing well. The problem is that building these models is very challenging for a number of reasons. One of them is that oil reservoirs are deeply buried. So the data we have to describe them is very sparse. And to give you some idea of how deeply buried they are, if you think of the tallest building in London, the Shard, 310 metres. Okay, if I take a typical oil reservoir, nothing particularly special about it, think about the Witch Farm field, which lies underneath Poole Harbour in Dorset. The main reservoir there is buried at a depth of 1.5 kilometres. That's 5 shards stacked one on top of the other. We have to get through all of this rock before we even get to the system of interest. So getting data from there is very challenging. We have to be creative in how we use it. So the first problem is we don't have much data. The second problem is that the systems are actually quite large. Think about how big an oil reservoir is. Again, what I have here is a Google Earth image of London. You can see it. We are sitting just about here by Hyde Park. And if we go off west, we go into Shepherd's Bush. Then we go into the city just here. And then this is the Docklands, the Dome, and out to City Airport. If I take that same reservoir, the Sherwood Reservoir, nothing special about it, kind of a typical example, and I superimpose it on London, it's about 18 kilometres from east to west, and about 5 kilometres north-south. This is a big area, this is a big volume of rock we have to characterise. And there's about 100 wells in the Sherwood Reservoir. So if you imagine, we're going to blindfold you, and we're going to take you to 100 different locations in London, take your blindfold off, and you can look around and see what's there. And then based on those 100 observations, we're going to ask you to reconstruct the street map of London. That's the kind of challenge we face when we're trying to build models of oil reservoirs. We have sparse data and complex systems. Complexity is the next thing. Okay? There's a great episode of The Simpsons where oil is found underneath Bart and Lisa's school. And in The Simpsons, the oil's in this huge cavern underground. If only that were true. In actual fact, in real reservoirs, the oil is hosted in tiny pores in between the grains of the rocks. There are billions of these pores in the reservoir, and the oil and gas has to flow through these tiny pores to the nearest production well. And that's the process that we're trying to model to predict oil and gas recovery. And the key property for me, modelling flow, is the permeability of the rock. That's a measure of how easily the fluids can flow through the rock. The problem is that the permeability of different rock types in a reservoir can vary over orders of magnitude. Different rock types have very different values of permeability, and those rock types are organised in a very spatially complex way. But I have to be able to model that spatial complexity to be able to properly predict how oil and gas will flow in a reservoir. So that's the challenge. What's my contribution? Okay, well, I actually don't work very much on subsurface reservoirs. That's the job of oil companies that operate those reservoirs. I look at analogue rocks which are exposed at the surface. And the advantage of that is that we have lots more data to work with. We can see the rocks in front of us. So we can study them in detail and build much more complex and detailed models. And we can look at these analogue rocks because the processes that led to their formation are similar to the rocks deeply buried underground. They were deposited in similar environments, so we see similar geometries. They're not exactly the same as the reservoir rocks, but they have similar geometries, similar generic features, which which allow us to use these as a proxy for the deeply buried reservoirs to understand how the geology impacts on the flow. Now, there is a spin-off benefit of this, which is that you get to travel to some really nice places. So here's an example. This is the western desert of Egypt, sadly off limits at the moment. We have some spectacular rocks, which is why we're there. We also have some spectacular culture. So there are all kinds of ancient, in fact some of the oldest ancient Egyptian monuments are found in the western desert, very rarely visited by tourists. It's a great place to go. Clearly, while you're there, you should immerse yourself in the local culture. This is, after all, an adventure. Although, perhaps just how much you immerse yourself, well, read the menu carefully. That's all I would say. So, I'm going to just show you one example. We've done lots of projects at this time. I'm going to show you one example to get a flavour of the kind of work that we do. This is looking at some rocks in Utah in the United States. We're near the small town of Green River. This is the Green River flowing through here. And you can see this amazing, sort of spectacular series of outcrops. These are called the Buck Cliffs. A stunning location, really a mecca for geologists the world over. The particular part of the section we're interested in is just here, where you can see, if we zoom in, that rather conveniently, the way the rivers have eroded in to the cliffs gives us quite a nice three-dimensional control on the geological architecture. Now, obviously, normally working with cliff faces, you tend to get a very 2D data set, but here we have the ability to project that 2D data into the third dimension and build 3D models. So I'm going to just show you a picture of the rocks that we're working on along this cliff line just here. This is called Battleship Butte. And we're actually working on this particular interval of rock here called the K4 power sequence. And those of you with very keen eyes might just be able to see there's a series of surfaces that cut down from left to right as you look at this. If you can't see them, don't worry. If you can see them, keep them in mind, because we're going to think about those again a bit later on. And just to comment on how these rocks were deposited, okay, if we go back to the Cretaceous, which is when these rocks were formed, the US looked very different. So this is about 100 million or so years ago. This is the modern west coast of the US. What we had back in the Cretaceous was a mountain belt coming through here. That's the same as we have today, the Rockies. But we know we don't. What we have now in the central part of the US is the Great High Plateau, which is where we have Utah and Colorado. That wasn't there. We have the seaway. Sea level was higher relatively. And the rocks that we're looking at were deposited in a shallow marine environment just here. And many reservoir rocks around the world were deposited in a similar environment. So this is a good analogue to understand those deeply buried reservoir rocks. So what do we do? I'll just briefly give you a flavour of this. The first thing is you have to collect some data. For that you need a lot of young, fit, active students. And their job is to hike up these canyons, scramble up the cliff faces, take lots of photographs, log what you can see, and bring it all back to us sitting in raised bar in Green River. You might need to supplement that. You might need an aircraft or a helicopter to get out to some of the really inaccessible cliff faces. And then you need to spend, again, students called for here, a lot of time diligently tracing out the key geological features along all of this data you've collected along the cliff faces. And once you've done this, you might end up with something that looks a little bit like this. And what we've got here is the tracing of all the key geology along that three-dimensional cliff outcrop that I showed you before. Once we have this, then we can start to fill in the gaps in between. So we can start to model key surfaces through here. And what we end up with is a 3D model of the geology of interest. And particularly here, we've got these different rock types, which are shown in orange, yellow, green, and grey. And this shows us that this is showing a modern day cliff line which we built this model from. You can see it's very strongly vertically exaggerated. What do we use this model for? This is where I start to earn my corner, okay? Because we can use these models as a numerical laboratory to simulate hydrocarbon production and begin to understand how the geology will impact that. So this is a typical example of a simulation. I've taken out all the rock above, all the rock below, the rock to the left and right. We're just focusing on the reservoir rocks of interest. You see there's a tilt, and we have a line of wells here that would go right up to surface, and these wells are injecting water, and that's a very common way of producing oil. To inject water to flush the oil towards the production wells and maintain the reservoir pressure. We have this would be down dip injection, and we have these production wells up here on the crest of the reservoir at the highest point. And the idea is that as we inject water, what we want to happen is for the oil to be swept out uniformly towards production wells and to leave none behind in the reservoir. Alas, that's not what happens in practice. And the reason is that geology messes things up. So, a typical problem that a geologist might have if they're trying to model a reservoir would be that they might have two wells, and they can see the rock types that they have at each of those wells. But the question is, what's in the middle? We don't have any direct data that will tell us that. So you have to have some conceptual model and a modelling process that would allow you to fill in the gaps. And perhaps the simplest way of doing that would be to assume that the rock types are just laterally continuous between those two wells. You might have a model that looks quite layer-caked, and lots of real subsurface reservoir models in this type of environment would look like this. What we can see though from our outcrop model, where we have all of this high resolution data, is in actual fact a lot more complicated than this. And these red surfaces you can see coming through here, those are the surfaces that I was pointing out in the outcrop photograph. These are called clinoforms, and they have quite a significant impact on the way in which these different rock types, represented by the different colours, are spatially distributed between those two wells. And the question is, does this really matter in terms of predicting hydrocarbon recovery? So we can do some experiments now, we can simulate it and find out what's going on. So here we have, this is our outcrop model with all the complexity here, this is our subsurface type model here, and we're showing some, again, we're injecting water, producing oil, the water's in blue, the oil is in orange. I've stretched the models vertically so you can see what's going on, and I've removed the dip. So if we play this little movie through, this is kind of my basic way of doing movies in PowerPoint. So we'll keep pressing the next slide. What you can see is that the water that we're injecting is moving very rapidly through this orange unit up here, and that has the highest permeability. So we get early water breakthrough with the producing wells. That water is now going to start being produced at surface. But if we keep playing through the simulation, what you can see is that actually we then have a sort of a secondary front of water that comes through here and rather efficiently sweeps the oil out. That's what we would predict from our subsurface type model. If we look at the model that's based on the outcrop data, it all looks a lot more complicated than that. So we have all of these areas where we've swept out the oil, it's gone blue. We have these areas of oil that's been left behind, it's been bypassed, which we can still see here in orange. And we can maybe begin to understand now why we're not recovering as much oil as we might have expected. The geology is playing quite a big role in controlling how the injected water can sweep out the oil. And we can compare this with some observed data. So this is data from the Brighton field. So, well-known field in the northern North Sea. And this is a series of wells that were drilled at the crest of the Brighton field. These were producing wells. And what I want to focus on is this one just here. What we see here are the colours showing the fluids that were there after 20 years of injecting water to produce the oil. So we've got some oil still, then we have an area where we've swept out, that's blue water, then oil, water, oil. Compare that with the predictions of our simple layer cake, simple subsurface type layer cake model. It all looks like it should have been uniformly swept out. So this comes as a bit of a nasty surprise. This is what your model's predicting, this is what you actually get. Ouch. My predictions have been quite wrong. Compare that against the model that we have in the outcrop, you can see something that looks a lot more like the sweep pattern that was observed in the reservoir. And actually, these dashed lines here, these are the cliniforms that a colleague of mine, Gary Hampson, identified in the wet field. They represent, you can see these here in these red lines in the simulation model. You can see these changes in saturation are associated with the cliniforms, and they are in our simulation model as well. So we can begin to see how some quite subtle geological heterogeneity have quite a big impact on how oil and water flow during production. And this helps to explain partly why we might recover less than we would originally have hoped, but also it helps us to understand where the oil we didn't produce is left behind. And that's important information if we want to try and engineer the field to improve the amount of oil that we recover. For example, we might want to drill some more wells. This would help us to identify where in the reservoir that bypassed oil has been left behind. Okay, so this is research that we have done. I want to say a little bit about something that we're doing at the moment. So there's going to be a mix in this talk of sort of things we've done in the past and things that we're doing now. I've talked about simulating flow using numerical methods. And we actually used a piece of software which is sort of used everywhere in the industry. It's called Eclipse. And it's the standard reservoir simulation software. And back in the early 1980s, there were a group of very clever people who were actually at AEA Technology. And they then left and joined a consultancy firm called ECL. And they developed this simulator for the first time. ECL's implicit simulator for engineering, or as they always said informally, implicit simulator of everything. Now, the thing is, if you look back at the 1980s, you know, we were listening to tapes on our Walkman when we were out and about. 2010, on our iPods. We were just about talking to each other on the first brick mobile phones. Now we have our smartphone. These guys at ECL were developing this fantastic new simulator called Eclipse. Flash forward to the 2010s, and here we are still using it. So in terms of reservoir simulation, it doesn't feel like Back to the Future, it's forward to the past. Now, I don't want to sort of, you know, Eclipse is a very robust piece of software. It's the methods, the numerical methods that underpin it that I'm interested in. And one of the big limitations of those is that we have to try and represent geology on a grid. So we have to subdivide the reservoir that we're modelling into a very large number of small rectangular or close to rectangular grid blocks. And we see an example of this kind of model here. Each of these grid blocks has a different value of permeability in it, from high perm in red to low perm in purple. The thing is that geology doesn't look like this. It's very difficult to model complex geology by having to subdivide it into very large numbers of small rectangles. Essentially what we're doing is saying, I've got some geology here, and I'm going to try and build a Lego model of it. It's the same principle. So here's a Lego model of a reservoir that we built at home. It's got some geology in there. So there's a fault that comes through here, and we've got some high perm layers that might be channels. It's not geology. This is not a good way to try and represent geology in a simulation model. If you look outside the world of reservoir modelling, they don't do this. So if I want to build a CAD/CAM model of a motorbike, or a bioengineer who wants to model a brain, or an aeronautical engineer who wants to model a plane, I don't use little rectangular cells. I use a much more flexible way of discretizing space. And I think if I showed up in an aeronautical meeting with my Lego model of a plane, they would laugh. But we do this all the time at oil and gas conferences. So what we've been looking at here is something that's different. What we're thinking about is discretizing the reservoir using a much more flexible approach, but also allowing the grid to change in time and space. At the moment, in a standard reservoir simulation, I have the same grid resolution throughout time. But the thing is, in real reservoirs, there will be parts of the reservoir where there's very interesting things happening, and I might want to have a higher grid resolution there, and parts of the reservoir where there's really not very much going on, and I can have a much coarser grid resolution and not lose any key information. So what would be sensible, I think, would be to allow the grid to refine in time, to focus on where there's interesting things going on and not where there aren't interesting things going on. There are people who are doing this already. So this is some work done by the Applied Modelling and Computation group here at Imperial. This is not a reservoir simulation. What we have is a column of water in a cube, and it's just going to collapse under its own weight. So sort of slosh around. This is actually solving the governing flow equations to do this. The thing I really want to point out is that the mesh will not stay fixed with time. It will adapt to capture the really interesting features. So if we play this, the way it sloshes, and you can see the mesh adapting, and the really interesting part of the problem here is that air-water interface. And where it goes dark, you can see this is where the mesh is fine. It's having to capture that sort of sloshing motion of the air-water interface. It's capturing these little droplets forming. This kind of simulation would be impossible if you try to do it on a fixed grid. The adaptive capability of the mesh is essential. So the question is, can we steal this and use it in reservoirs? And that's something that we're looking at right now. So a little bit less impressive, but this is a model of a very simple reservoir, the kind of thing that engineers like. We have one low permeability rock layer and one high permeability rock layer. And we're going to inject water over this face, and we're going to see what happens to the simulation. So if I play this, what you can see is that the water, as you'd expect, starts to move more quickly through the high permeability layer. And the bit of, oops, don't press the wrong button. So the bit of the solution that's really difficult to capture is this contact between the injected water, which is rather confusingly in yellow, and the oil, which is rather confusingly in blue. That sharp interface there is what we really want to capture. And you can see how the mesh is adapting to be very refined in the vicinity of this contact, which is hard to simulate. And it's coursed ahead of that, and it courses again behind, so we're focusing computational effort where it's really needed to capture the key parts of the solution. It's this kind of thing that we're looking to bring into the reservoir simulation workflow. This is current and ongoing research. Now, this first chapter was called Rocks and Oil, but I've already talked quite a lot about water. So we've been injecting water to encourage oil production. We've worried about water being produced at the wells. And this really leads me on to the next chapter, which is rocks, oil, and water. So everything I've talked about so far has been about modelling what's happening in the reservoir. But modelling has its limitations. We have a scarcity of data, and so the predictions of models are always going to be uncertain. So one thing, if we're worried about water, and we should be, it's a big problem for the industry. On average, the oil industry produces 3 barrels of water for every barrel of oil. And this water is not useful, it's normally saline, it's normally contaminated, it's expensive to treat, it has to be disposed of. It's also very energetically kind of wasteful to bring all this fluid to surface, all this water to surface when we don't really want to. It'd be better to leave it in the reservoir. So we can try and model where the water's going, but there's going to be uncertainty in those model predictions. So you sort of think, well, wouldn't it be better just to monitor where it is? Are there not some monitoring technology we can use which will tell us where the water is in the reservoir? And the answer is no, not really. We can use seismic. So seismic is where we would fire acoustic waves into the earth. They get reflected from the rock layers and come back to surface. You can sometimes pick up oil-water contacts, but you probably wouldn't be able to do it at particularly high spatial resolution, and you wouldn't be able to collect the data very frequently. And there's not really very much else out there. So we've been looking at a method to monitor water movement, which is based on measuring something called self-potential. Now, I'll say a little bit about where that comes from. If we have, I talked about the oil and water being held in these tiny pores in the rocks. This is 2 of these tiny pores, blown up so they're enormously large. This is the mineral surface, and this will be filled with pore fluid. Let's say that's water. What we know about water is it contains ions, things like sodium ions, chloride ions. These are charged, they've gained or lost some electrons, they're electrically charged. And what you might expect is those ions will just be distributed randomly throughout the water. What you find is that that isn't true. What happens is that the surface of the mineral is electrically charged, so we have an excess of positive charge. The minerals are normally negatively charged, and that attracts some positive charge from the water and repels some negative charge. So we have this net excess of positive charge in the water next to the mineral surface. The system as a whole is still neutral, we've just redistributed the electrical charges. And if we then impose a pressure gradient, then we drag some of those excess charges along with the flow. This generates an electrical current, which has an associated electrical potential. This is the self-potential which we can measure in the earth. Now, I feel like I'm doing something risky here, but I've talked about this lots of times. Very few people have actually seen it in action in an experiment. So that's what we're going to try and do now. Right. So, oops, right, here we are. What I'm doing is, what I have here is a pressure vessel, some safety glasses. Okay, and inside this pressure vessel there's a piece of rock that looks like this. It's called a plug. Okay, and it's very tightly confined. So if I have to pump any fluid through here, it goes through the plug, not around the side. Okay, and I have two reservoirs. One of which is going to deliver water, seawater, into this plug, and the other is going to collect it. And I'm measuring the pressure on each side of the plug, and the pressure difference is shown here by the blue line. I'm also measuring the voltage across the plug. I've got two electrodes that measure the voltage drop across this plug. And what I'm going to do is press the pump to switch it on. It will start to force fluid through the plug. We will see the pressure difference change because we have a pressure gradient driving the flow. And we're going to see what happens to the voltage, fingers crossed, across the plug. So here we go. Here goes nothing. Oops. I pressed the wrong button. Press 6 rather than 3. Yeah. Where are you? Failed. Here we go. Right, brilliant. So what did Martin say about I'm not one of these people who sits in the office and has some guy in a lab who actually does the work? I've just blown that out of the water, haven't I? Right, so what's going to happen is that this is going to keep rescaling here. So we're going to watch the axis change. We can see the pressure in blue already starting to change quite significantly. The question is, does the voltage change? All we're doing here is pumping water through this plug. Do we see a voltage response? And the answer is yes, we do. This is the voltage here. It was quite stable for a long time, and I started pumping here, and look how the voltage is starting to climb. So I'm generating this potential difference across the plug simply by pumping water through it in a very, very neat piece of physics. Okay, so the voltage is going to keep climbing. Eventually we'll reach some sort of steady state. You can see the voltage climbing up here, generated purely by the flow of water through this plug. Okay, all this effort for a 1 minute video. So I'm going to stop this now and talk about whether this is actually useful or not. But it's nice to actually demonstrate it for once rather than just talking about it. So if I stop pumping, I know how to do this one, then what we'll see is the pressure difference starts to relax and the voltage starts to come down as well. So we can see this voltage is clearly changing in response to the pressure difference in the flow through the plug. Okay. What can we do with this? Flick right through the presentation again. Right. This is when my animation's very irritating. So we've seen that we generate this electrical potential. Is it any use? Well, we do lots of laboratory experiments to investigate this. We also do some numerical modelling. This is the results of that numerical modelling. This is simulating oil production from an oil reservoir. And what we have here are 3 sections. These are 2-dimensional sections through a 3D model at different snapshots in time, early, middle and late. And we're seeing water saturation here. The water is in grey and the oil is in white. And we have a production well just here. And the water is exploiting a high permeability rock layer. And that's why it's preferentially fingering through. And the thing is that this rock layer does not intersect the well. So you'd have no idea it was there. The first thing you'd know is that suddenly water had arrived at your production well and you weren't expecting it. If, however, you'd been measuring the self-potential along the well, you'd have seen it coming in plenty of time. What we have here are plots of the self-potential measured along this well at these same snapshots in time. And what you can see is that the potential that you measure starts to change before the water arrives at the well, and moreover, it starts to change in a way that tells you where the water is. So you wouldn't have to be an expert interpreter to look at this curve and say, that's where the water's coming through. There's a direct relationship, in fact, between the magnitude of the change in SP and the distance and shape of the waterfront. So we can use this to start to monitor water movement in the reservoir by instrumenting the production wells with fairly simple electrodes. In terms of the financial incentives for doing this, this is some results from a slightly different study, but they're kind of indicative of the potential benefits. This is the net present value. This is a measure of the financial value of a project. And for an oil field development with 3 different control methods, this is just controlling the wells on the surface. Then we have the kind of downhole monitoring and control capability that we've just talked about, where you can see the water coming. And then this would be an approach based on reservoir engineering common sense. So the first thing to notice is that the numbers here are eye-watering. So this net present value is measured in US dollars. This is billions of dollars. So the value here goes somewhere between 2.5 and 4.5 billion US dollars. It's a good business to be in. What we plot here is the NPV gain of using this kind of control versus just using reservoir engineering common sense. And this downhole control capability, and I should point out these different dots represent different unexpected reservoir behaviours, so different unpredicted production performance. And we can see some significant gains in NPV from having this kind of hardware downhole compared to the way that we would do it conventionally. NPV gains of up to 50%. A 10% gain in NPV here is about $100 million, so this is well worth doing from a financial perspective. So what are we doing now, though? So I'm going to talk a bit about current research. This has a much more environmental sort of applications. Now we're going to be looking at the south coast of the UK. So we've got Brighton just here, and in common with much of the south coast, Brighton sources its drinking water from an underground aquifer, the UK chalk aquifer. The problem with this is if you're near the sea, okay, if you take a cross-section from north to south, going from on to off the shore, you see something that looks a bit like this. Okay, this is the chalk. Okay, Brighton is around about here. This is the channel. And you have fresh water recharging the aquifer from rainfall on the South Downs. You also have this saline water in the aquifer here. And in equilibrium, the balance will be driven really by the density contrast, the amount of recharge coming from the South Downs. If you start to produce fresh water from the supply borehole, the risk is you can draw this saline water into the aquifer. It will reach the production well, and that will go saline. And then you've lost that very precious freshwater resource. And the way that the seawater responds will be through a fracture network. The chalk's highly fractured, so we're trying to capture that by this long, thin tongue of water coming through here. So it's very difficult to predict. So the question is, how do you know how hard you can produce these abstraction wells? Or how do you know where the salt water is? The answer is we don't really know. We don't know where the salt water is. We know that if we pump these wells hard, we're more likely to bring the salt water in, but how hard, we don't know. So there might be some rules of thumb. You might not pump each side of high tide, for example. So the question is, can we monitor where the salt water is using these measurements of self-potential? Okay, so we've put some electrodes in this observation well here. There's actually an active abstraction well for Brighton just here at Ballsdean. If this goes saline, this is a big problem for Brighton. Salt with efficiencies. Okay, we're about 1.5 kilometres away from the sea here. At our observation well, this is us putting the electrodes down. There's Jan again, doing all the hard work. And Donald John, one of the PhD students, and this is legs. It's fairly simple equipment, just an array of electrodes connected to a recorder. And this is the sort of data that we've got so far. So this is over about a 4-month period. This is the voltage, measured the electrodes. The different colours represent different electrodes in the borehole. And it looks very, very zigzaggy. we can do an analysis to look at the period of those zigzags. And if we do that, what we see is that most of the zigzags sit with a fluctuation that occurs twice a day, this semi-diurnal cycle. What else happens twice a day? The tide comes in and the tide comes out. And we see a peak as well over this fortnightly cycle. We go from neap to spring to neap tides. So what we think we can see here is that the saltwater front, it doesn't reach the borehole during this monitoring period. So we're monitoring the saltwater movement at a distance. It never actually reaches the borehole. As the natural tidal cycle brings the salt water closer to and further away from the abstraction well, so we see this oscillation in the SP that we measure. Now we're just doing this in observation well at the moment, so the salt water is only moving because of natural processes. But clearly if we do this in abstraction well, and we're causing the salt water to move in response to abstraction, we should be able to see it in just the same way. So this could be a method for controlling and managing water production in these saline aquifers. And this is a huge problem worldwide. Millions of people have drinking supplies that are at risk from saltwater intrusion. This is a relatively cheap technology that can be used to address that. Okay. So the final chapter, volcanoes. Now here we go. This has got to be the whiz-bang stuff, surely. I mean, you know, this stuff about saltwater in Brighton and looking at rocks in Utah is all well and good. Volcanoes, eruptions, Pompeii, people dying. It's not quite what I do. Okay, so I'm really interested in what happens under the volcano. So we're looking here at a sort of a very simple model of a magma plumbing system in the crust. Okay, so the crust here, this is the continental crust, is about 30 kilometers deep. Could be more than that, could be less than that. Everything I've talked about so far is really in the upper 2 kilometers. So we're going to much greater depths now. So we have this crust. It's like the hard, crunchy outside, and it sits above the warm, gooey inside of the earth, the mantle. And what we think happens with these sorts of magma plumbing systems is that we have a lot of hot rock that comes in at the base of the crust from the mantle, and it causes some partial melting of these rocks. These magmas can then move up through conduits like fractures or faults. They might pond in magma chambers at shallower levels in the crust. There might be more cooling and crystallization, and eventually we might erupt some magmas out the top and form a volcano. Now when I say magma chamber, even I sort of think, yes, there's a big hole in the ground full of magma, like the Simpsons model of an oil reservoir. In actual fact, that's probably not the case. It's very difficult to sort of thermally, you have to have a lot of heat coming in to keep a magma chamber magma. It tends to cool and it crystallizes. So there's increasing evidence to suggest, certainly I'm convinced by it, that most of the time magma chambers are full of a mush, kind of a mixture of crystals and melt. The melt is along the grain boundaries between the crystals. That sounds a bit like an oil reservoir now all of a sudden, because there we had solid rock grains with oil and water along in the pores. Now we've got these crystals with melt in the pores. And every so often, through some natural process, it might be driven by buoyancy or it might be driven by stressors in the crust. Some of this melt naturally moves up through a conduit to the Earth's surface. In an oil reservoir, we put that conduit in, we drill a well. But again, it sort of feels quite similar. This feels a bit like, quite analogous to an oil reservoir system. Mush, melt, same. So although volcanoes and oil reservoirs might sound very different to me in terms of the physics of the flow, they're actually quite similar. So I also look at analogues. I don't work on modern volcanoes, too dangerous. So you can go to places where there are fantastic examples of ancient magma chambers that are long since cold. They've been exhumed and brought to the surface. One example of this would be Rum, an island off the west coast of Scotland. This whole area, about 50 million years ago, was full of volcanoes. The evidence for that is all over the place. You can see lava flows. The Giant's Causeway is an example of this volcanic activity that we still see today. And we can study these ancient magma chambers as an analogue for modern magma chambers and the processes that occur in them today. So we're drawing to the end of our bedtime story, so I won't say too much about this. I'm just going to show a couple of examples. So the first is a very shallow example. We're going to look at a lava that's cooling. And you can do some chemistry on this. You can measure some chemistry. And you can look at how that varies with height through the lava flow. So this would go from the base of the lava flow to the top. And we can look at two different types of chemical signature. The incompatible ones would tend to partition would stay in the rock. Would partition into the melt. And the compatible ones would tend to stay in the solid rock. Okay, and we see these characteristic S shapes. This dashed line here represents the original composition of the magma, and this represents what we see now crystalline into place. We see a depletion of the incompatible elements at the base, and then a relative enrichment towards the top. And it's the other way around for the compatibles. We see an enrichment at the base and a depletion at the top. So the question is, can we model this? Okay, so we're going to see a little animation now. This is showing we've got our lava flow from base to top here. We're going to see temperature through the lava flow. We're going to see melt fraction, porosity basically, the amount of melt that's locally in the system. And we're going to see the composition here. It's going to cool from above and below. So we see the cooling moving down, the lava flow is cooling, the melt fraction is evolving, we're starting to change the composition that's preserved in place. This is that's happened. This is what we get at the end when the lava is completely cold, or at least it's no longer molten. We can compare these sorts of signatures with what we observe in nature. So you can see that for the incompatibles, we have a relative depletion at the base and an enrichment at the top, and we see an enrichment of the compatibles at the base and a depletion at the top. And that's exactly what we see in natural systems. So we can start to model this by looking at melt percolating through this mushy crystal pile. The last example I'm going to talk about is one from very deep in the crust. This is still current and ongoing research. What we think happens here is that we bring in lots of hot rock from the mantle and it starts to melt the overlying crust, and we get magmas that leave that system and move up to shallower levels. And again, we can look at this, we can model this. So here we're looking at a situation where we've got hot magma coming into the base of this model. We're going to model the temperature evolution, the evolution of melt fraction, and look at the compositions. So if we play this, we see we're heating from below. We can see the melt fraction evolving, and it forms this big, high porosity melt lens at the top of the system. I'll let that play one more time. There we go. And this big melt fraction here, this is a melt fraction about 50%. This could be tapped and moved through a fracture or a fault system to higher levels in the crust. The question is, what's the composition of the melt in this lens? So we can predict it from our model. This is looking at one of these incompatibles that would tend to move into the melt, one of these chemical traces, chemical signatures. And if we look at the enrichment of this incompatible element that we predict from our model, it sits around about here. Now there are some existing chemical models that try and predict what's going to happen here. They don't account for the physics of flow. They don't account for the melt moving compared to the crystal pile. And they predict a much greater enrichment of these incompatible elements than we actually see where we capture the physics of flow. Now this has some pretty profound implications because we use these sorts of chemical models to try and understand where magmas came from. And if those models aren't accounting for the physical process that leads to the formation of those magmas, then we're going to be making some incorrect interpretations of where those magmas originally came from. Okay, so that's just a little flavour of the sort of research I'm involved in. I am aware that we've covered a lot of ground in the last hour. To be honest, if you remember 10% of this, I'll be happy. In fact, if all you remember is that I once appeared on TV dressed as a chicken, that's fine. And after a talk like this, I don't really have any big picture type conclusions. I guess all I'd say is that I think I'm very lucky in that I really enjoy what I do. I get up, I come to work. There's a whole range of fascinating problems out there, and I want to get stuck into them. And I'd also say that I am surrounded by a fantastic group of people here, and I'd like to acknowledge the contributions of all of those people, especially those who can make the pump work. who have contributed to what I've been working on in the past, the present, colleagues, PhD students, postdocs. Without this, without you, I wouldn't be standing here now. And I'd just like to say thank you very much.
Well, it forced me to give the vote of thanks, and it really is a real pleasure to be able to say thank you to Professor Matthew Jackson for an enthralling lecture that I think you'll agree with me covered a lot of ground and really allowed Matt to roam free across his range of impressive disciplines. To me, it's astonishing. The astonishing thing to me about Matt, I've known Matt for a long time, is his versatility and his ability to work with colleagues across a range of disciplines. I think what allows Matt to roam in the way he does is his very deep understanding of the physics of natural processes related to the Earth. So a really uniting force. It's helped me in my work and others as well, so I've been testing that insight. I first met Matt when we interviewed him, I don't know, early 1990s, I guess, as a young PhD student who just left Imperial Liverpool University, and there's three of us, I think, in the room, talking, asking some questions as you do. Somebody made the mistake of asking Matt about fluid viscosity. Did he know anything about it? I think within about 30 seconds, he probably knew far more about it than anybody in the room there at that time. And he's sort of developed his understanding of that since then. I think one of the names of lists was a chap called Mike Atherton, who would be close to Matt's hire at Liverpool, one of the part of the supervisory team. And Mike was pretty rough with Matt, because Mike was a geologist, Matt was a physicist. We went on a field trip to Donegal, Matt, you might remember. And Mike was pretty rough. He was saying, you'd pick up a rock or a stone and you say, Matt, what is it? What's in it? And you'd have to go through the minerals with him, because in a childlike way, like learning a language. But very quickly, Matt got the hang of it. I think that introduction to geology and the speed in which he grasped that is something which I think he's taken to other disciplines as well as he's worked on across science. Matt, I have to say this because the chicken is partly my fault, because when Matt was a PhD student, it was my wife's company who actually worked for Liverpool Victoria, who put on the chicken escapade. And in fact, Matt, I can add to your list of possible successes that never happened, and that's snooker. Because Liverpool Victoria, in fact, the whole line dance of the chicken that Matt was in, it was the biggest line dance ever. Ever. And Matt was a key chicken in the line dance. It was all to do with snooker sponsorship. And I think there was a point when the head of Liverpool Victoria, the marketing person, fell out with Matt. So I think you can imagine Matt dancing in a chicken suit. After a couple of hours, the environment inside gets a bit ripe. And I think he refused to go back into the chicken suit. And I think Carol Borick, her name was at the time, the director of snooker, made the immortal quote to Matt, which I will have to share with you in this room. She said, Matt, if you don't get into that chicken suit, you will never work in snooker again. And she was right. And I think, Matt, it's been downhill since then, hasn't it, really? But I mean, just to echo Martin's comments at the beginning, Matt is a real asset to the college, to the university here. And just to wish him well in his future career, can we just thank him one more time? Thank you, Matt.